Okay, so this is our first lesson on logarithms here. I've gone past the exploration stuff and I'm on page 184. We're going to do some examples here. So the x-intercept of any graph that has y equals log base b of x is 1. There is no y-intercept. The y-axis is a vertical asymptote with the equation x equals 0. The domain is x is greater than 0. The range is y is any real number. So remember, this is the inverse of an exponential function. So our domain and range have switched. We now have a vertical asymptote at x equals 0 rather than the other way around. Y equals log base b of x is equivalent to x equals b to the y, an exponential form where x is greater than 0 and b is greater than 0 but not equal to 1. B is the base of both the logarithmic function and the exponential function. Since the logarithmic function y equals log base b of the x is only defined for positive values of x, the logarithm of a negative number cannot be determined. The logarithmic equation y equals log base b to the x can be expressed in the exponential form x equals b to the y. The exponential equation of y equals b to the x can be expressed in logarithmic form as log base b of y equals x. State the inverse of the following functions. Answer in the form y equals. So this is one that often tricks people here. We have the original function is y equals 3 to the x. So the inverse of this is the exponential function that has the same base. That is not the same as writing this function in exponential form. It wants the inverse of it. B, y equals 8x. Well, if we want to start the inverse like this, we know we switch x and y. Well, now to get y by itself, we need to write in log form. The base always stays the same. So the base of the logarithm is now a because the base of the exponent was 8. Next example, convert each of the following from logarithmic form to exponential form. So the key is the base stays the same. Our base is 7. We now have a power of 4, and this is equal to x. Same thing here, the base is 5. Base always stays the same. Our exponent is y, and it equals 15. Base stays the same, so base is t to the power of m equals b. D is a little bit trickier. We need to get our logarithmic form to look like it did on all the other questions, which means we need to deal with this 4 first. So if we divide both sides by 4, we now have this, and from here we can change it into exponential form. So the base is b. We now have an exponent of 5 over 4, and this equals 6. Next example, now we're going to go the other way, convert to logarithmic form. So the key is the base stays the same. So if I'm writing this as a logarithm, my base is 4, my input is now 63, and that equals 3. It allows us to get the exponents unlocked. We can get to those exponents now. So we have log base 2 of 1/8 equals -3. Base stays the same. Here we have log base e of f equals d. Last one looks a lot more confusing, but we can just follow the same pattern. So this is log base a, because our base was a here. Now our input into our logarithm is 2x plus 4, and this equals our exponent. Last one of this section, and then there's a few more after. Calculate the value of t if log base 2 of x equals 3 and log base 2 of t equals x. So whenever you're stuck in this unit, always convert. We don't really know what to do with this, so we're going to convert it to exponential form. So now we have 2 to the 3 equals x. Well, suddenly we have a value for x. They hid it in a complicated expression, but this was really just telling us x equaled 8. So now we're going to have 2 to the x equals t. Well, we know that x was 8, so we're going to go 2 to the 8, which is 256, which is equal to t. So the logarithmic form of y equals a times b to the x. We have seen how to change forms between the exponential form y equals b to the x and the logarithmic form log base b of y equals x. We now consider how to write the exponential form y equals a times b to the x in logarithmic form. This can be done using the following procedure. Write an exponential form, divide both sides by a, and then change. So here we have the logarithmic form of y equals a times b to the x. We divide out a, and now we follow our rule. Log, the base stays the same. Our input into our logarithm, or the argument of our logarithm, is y over a. And now we can get to that x. So 2 more examples here. Change each of the following from exponential form to logarithmic form. So here we divide both sides by 2. That gives us y over 2 equals 3 to the x. And now we can get to that variable x, which is really our whole point of logarithms, is to be able to solve for an exponent x. Okay, let's skip to D. So if we divide both sides by 2/3, that is really the same as, if we divide both sides by 3 over 2, that's really the same as multiplying by 2/3. And if we'd multiply the right-hand side by 2/3, the 3 and the 2 would cancel out, so that would get us what we want. Now I have 2/3 y equals 10 to the x, so I can rewrite that. Log base 10. Remember, if your base is 10, you don't have to write it. We're going to assume the base is 10. So we're going to have log 2/3 y equals x. That is a special case of logarithms. If there is no base written, we assume it's base 10. Kind of like how a square root sign, we don't put an index in, we assume it's 2. With a log, we assume the base is 10. Last one, change each of the following from logarithmic form to exponential form. So now we're going the other way and we want to isolate y. Well, we know our base stays the same and the other two switch. So we have 7 to the x equals y over 3. Now we can multiply both sides by 3. So we'd have y equals 3 times 7x. Same thing here, 10 to the x equals y over 4. Multiplying both sides by 4 isolates y. Do the same thing for the last two. This last one here is another special case where we have a base of e. That's called our natural logarithm. We'll get into that a bit more in the next few days.